webinar. Today I'm going to cover a brief overview on the HeliScan MicroCT and then go through a series of examples showcasing how CEMAS users are utilising the versatility of the HeliScan MicroCT to meet their research needs. Please feel free to ask any questions through the Q&A portal or the chat window during the talk. If they are more general questions, Daniel Vecti has volunteered to answer them. If they are more MicroCT specific questions, I'll come back to them at the end of the talk. I'm going to start by giving you a quick overview on my background. I earned my Bachelor of Engineering in Petroleum and Chemical Engineering from the Adelaide University in Australia. Since finishing my degree, I have gained over 7.5 years of work experience with the HeliScan MicroCT. I spent 5 years in Canberra performing MicroCT experiments on rock samples for oil and gas projects. Then I spent a year working at the Tyree X-ray lab at the University of New South Wales. And in June, I moved to Ohio and joined the CEMAS team in June 2018. That is, I joined the CEMAS team. CEMAS opened in September 2013 and was custom designed to be an optimized environment to perform microscopy experiments. We have around $40 million worth of equipment, including transmission electron microscopes, scanning electron microscopes, FIB-SEMs and other analytical machines like the MicroCT. In the center of the slide, you can see an image of the CT, a photo from our lab. On the right here, you can see the Aprio, and on the left, you can see the Titan. X-ray MicroCT is a powerful non-destructive technique that allows you to capture 3D information about your sample. MicroCT can be used to analyze samples before and after a lab experiment has been performed or as part of a multi-scale correlative study. It is also possible to run in situ experiments. However, we are yet to perform any at CEMAS. The HeliScan uses a flat panel variant detector with 3000 by 3000 pixels. The sample stage can hold around 15 kilos and has a vertical height movement of 195 millimeters. The HeliScan has a transmission X-ray source with 2 scanning modes. We mainly operate in the high resolution low flux mode using a Lab 6 filament. In this mode, the smallest achievable voxel size is 400 nanometers and the maximum tube voltage is 100 kilovolts. The other mode is the low resolution high flux mode with a tungsten filament installed. The smallest voxel size achievable in this mode is 800 nanometers with a maximum tube voltage of 160 kilovolts. This mode is really good for large dense samples. On the left of the screen here, you can see the photo from the previous slide showing the CT, inside of the CT. Below, you can see a schematic of the CT. So you've got the X-ray source, you've got a sample host and a Kinder Surprise chocolate as a sample, and you have the detector. In this schematic, the X-rays are turned on and you can see we're getting a projection captured on the detector. Now we're going to look at an even more simplified diagram for when I explain geometric magnification. This little yellow dot represents the source, the large grey circle represents the sample, and the rectangle represents the detector. If we turn the X-rays on and capture a projection of the sample, the X-rays that pass through the sample would fill up this amount of the detector. If we bring the sample physically closer to the source, we get a larger magnification. If we move the sample further away from the source, we get a smaller magnification. If we decide that instead of moving the sample, we're going to move the detector, If we move the detector closer to the source, we get a smaller magnification. And if we move it and then decide to move the detector even further back, we result in a larger magnification. However, there's a limit on how far we can move the detector from the source because the actual system is limited to about 835 millimeters of detector stage movement. This table gives you an estimate of the voxel sizes you can achieve with different sample sizes. The table, if you have a 5 millimeter diameter sample, it would be possible to get a tomogram with a 2 micron voxel size. However, if you decide you actually need an 800 nanometer voxel size to resolve your features of interest, you would have to think about either performing a region of interest scan. So instead of imaging your whole sample, you would just zoom in and image the center. Or you would have to, if you didn't like the idea of region of interest scan, you would have to think about physically reducing the size of your sample to get a smaller voxel size. When you're using the HeliScan, you have two choices. Well, you have, there's three choices for trajectories. You have the choice of using a space-filling trajectory, a double helical trajectory, or a circular. Both space-filling and double helical are helical trajectories. What that means, instead of just rotating your sample, it's also moving it in a vertical direction. This allows us to image samples with greater than 1:1 aspect ratio. So it's really great for long samples. In a circular scan, the sample stays at the same Z height and just rotates in a total 360, which means that if you have a long sample, you have to take many different circular scans and stitch them together. If you choose to use a space-filling trajectory, you'll end up using an iterative reconstruction code to recon your data. And if you choose the double helix or the circular, your data will be reconstructed using a filter back projection. All this reconstruction happens on the GPU cluster that is part of the HeliScan system. This diagram shows the acquisition and reconstruction, In this diagram, it shows you the workflow of sort of like, I guess, a MicroCT workflow. So you start with your sample, you scan your sample, you get some projections, you reconstruct your data, come up with a tomogram made out of different slices of your data, and then you can reconstruct it. And then you can visualize and analyze it. I like to separate this sort of workflow into two different sections. One of them is the acquisition and reconstruction stage. This is what actually takes place on the HeliScan. And then the second stage is the visualization and analysis. So when it actually comes to doing your scan, when you start, once you have your sample, you're going to come and you decide, do you want to image your whole diameter of your sample? In that case, it'd be a full field. If you want to try to get better magnification, you might choose to do a region of interest. Depending on what you want and what the size of your sample is, you'll also decide what trajectory you'll use. Once you've actually scanned your sample, so when you scan your sample, you'll get a whole collection of projections. Once the projections and the scans, once the scan is complete and all the projections have been taken, they will be transferred to the GPU cluster and reconstructed. Depending, as I mentioned before, depending on what trajectory you used, it will depend on what reconstruction code you use. Once the data is finished reconstructing, the final output data from the HeliScan will be a 3D grayscale tomogram. It will be exported in either a TIFF stack or an NC block. The next stage, once you have your 3D tomogram data, is to potentially do analysis and visualization of the data. There are a range of different image analysis programs available. CEMAS provides our users access to Aviso on our virtual machines, and OSU staff, students, and researchers have access to MyPar. So once you've chosen what software analysis program you want to use, you can load your data in and sort of segment and quantify it. There is a lot of online resources on how to do the image analysis. Avisa and MyPar both have very good online tutorials. MyPar even has an academy. The complexity of how hard the image analysis will be really depends on what type of sample you have, what the actual research goal you're trying, like what information you're trying to capture from that sample, and the quality of the image you acquired. Since the sample chamber on the HeliScan is not under vacuum, we are able to image samples that are wet. They can be partially or fully saturated with fluid. So if you have a sample that you want imaged and you want to bring it to CEMAS, please just ensure you bring the sample in a sealed container so that it doesn't drip into my system pretty much. And also when you have it in that sealed container, you want to make sure the sample's not moving. If your sample's moving in the fluid, you're going to end up with sample movement, and that's going to end up with double edges on your reconstruction. If you do have a wet sample, or really any type of sample, I'm always happy to discuss sample mounting with current users or future CEMAS HeliScan users, and I'm willing to help you brainstorm sort of different ideas on how might be the best way to mount your sample. Just drop me an email, and especially while we're all working from home, we can arrange a Zoom meeting. If you have a biological sample, if you stain them, fix them, stain them, and bed them, that will make it really easy for when you want to come and mount it onto the CT. However, they don't necessarily have to be embedded. However, we do ask, ideally, that they be fixed. Sometimes, due to your experimental constraints, you might not want to fix your samples. In this case, contact us and we can chat about it. Also, if you think there's any chance of your sample being BSL2, please contact us before you come bring your sample to CEMAS, and I'll pretty much direct you to talk to Sarah McCullough. Sarah is our lab manager at CEMAS, and she's in charge of the health and safety. She's also an expert when it comes to biological staining, biological samples, and also staining. Which brings me to the next point. If you have a biological sample, you might need to stain it to get enough contrast to see the features you're interested in on the MicroCT. And in that case, we can also chat to you about what might be the best ways to stain your sample. So that was a very brief overview of the HeliScan MicroCT. Now we're going to move on to the fun part of the talk, which is the case studies. To start with, I wanted to share this graph with you, which shows sort of the range of different samples that we've imaged here at CEMAS. On the left, you can also see a list, which is not an exhaustive list. There's other departments that have used us, but a list from OSU and also external research departments that have actually used the HeliScan to help them solve research problems. During this talk, I'm going to highlight 5 different samples. A B Mandeville. We're also going to look at a titanium alloy powder, a sandstone, an additive manufactured sample, and a mouse heart. For all the examples I'm going to show, I'll mostly be showing 2D slices from the tomogram, and in some cases I'll also be showing volume renderings from the tomogram made in Avisa. For instance, these 3 images are all 2D images from the tomogram, and the mouse heart and the B are both volume renderings of the data. So we're going to start with talking about the honeybee. And while I have it on the screen here as a volume rendering, I just want to point out where the mandibles are on the head. So this feature here, I'm hoping you can see my mouse, is one of the mandibles. And then just behind it is the second one. These use their mandibles a bit like we use our teeth for our hands, for tasks involving biting, picking up and moving items, biting and physically breaking down surfaces. Dr. Hongmei Li Balei from the Honeybee Research Lab at Central State University is using the HeliScan here at CEMAS to compare the morphology of mandibles from different species and subspecies of honeybees to see if a difference in morphology of bee mandibles influence the mite-biting behaviour of honeybees. Studying the mite-biting behaviour in honeybees is important as it's the way the bees defend themselves against varroa mites, which can transfer a potentially fatal disease to them. For the initial scans, the bee mandibles were dissected from the bee head and scanned as pairs with a voxel size of 2.6 micron, with each scan taking approximately half an hour. The image that's just appeared is a 2D slice from one of the tomograms. On the left here, you can see one of the mandibles, and on the right, you can see this other mandible from the same bee. We scanned over 30 bee mandible pairs in this way. The MicroCT data was then loaded into a VISO, where the mandibles were visualized in 3D by using the volume rendering tool. The measuring tool was then used to measure lengths of the features of interest. Following the success of these scans, 20 bee heads were imaged with a voxel size of 5.5 micron and a scan time of approximately 1 hour and 10 minutes. On the previous slide, you saw a short animation sliding through the Z slices of the tomogram from the bee head. And this is a volume rendering that you saw also previously of the data set. Having the scan of the whole bee head allows Hongmei to gain information not just about the mandibles, but the overall head structure of the bee. Now we are going to move on to a titanium alloyed powder sample. This powder is used as a feedstock for laser additive manufacturing. Shuram from Material Science Engineering is scanning this powder to gain information about the shape and size of the powder particles, and also to gain information about the porosity of the powder, the porosity within the actual powder particles. To image the powder, it was poured into a small glass capillary and then mounted on the MicroCT. The sample was scanned with a tube voltage of 100 kV, and the scan time took around 3 hours. The images on the screen show a vertical slice here and a horizontal slice from the tomogram, and the tomogram had a voxel size of 1.7 microns. In these images, you can clearly see the porosity within the particles, and I've pointed out a few locations here with the yellow arrows. In the ones that are pointed to with the arrows, you can mostly see, at least on the slices we're looking at, the porosity looks enclosed within the particle. But you can also see, as pointed by the red arrow, that some of the porosity, some of the pores within the particles look like they actually break the edges. Now that Shuram has the MicroCT data from this sample, to gain a more quantitative information, it would be necessary to analyze the data in a program like a VISO or MyPar. In a VISO or MyPar, it would be necessary to segment out the particles and also the pores, and then it'd be possible to use the inbuilt measurements filters to calculate different volumes and different measurements of interest. Our third sample today is a geology one. Dr. Julia Sheets of the Subsurface Energy Materials Characterization and Analysis Lab here at OSU is using the HeliScan to image small rock cores from the Rose Run Formation. This formation is located in the subsurface of eastern Ohio. On the screen, you can see a central vertical slice and also a horizontal slice from the MicroCT tomogram. The samples are complicated sandstones with detrital quartz and feldspar, dolomite as grains and cement, and clay mineral stringers with traces of iron and Fe and Ti oxide phases. In this image, for this scan, we imaged the sample in an NMR tube. This little break here is just a crack in the tube. This animation shows how the sample changed as we move along the z-axis of the tomogram. In the next step in the experimental plan for this sample is to expose them to brine with sulfur species in the lab. The sample will be re-imaged on the HeliScan, and comparison between the before and after exposure images will enable Julie to determine the changes in mineralogy and the pore network of the rock as a result from the brine-rock interactions. This information will be used to help inform subsurface models. For our fourth sample today, we're going to look at using the MicroCT to look for defects in an additive manufactured component. Dr. João Oliveira from the Department of Mechanical and Industrial Engineering at Nova University Lisbon and his collaborators are reviewing non-destructive methods to detect defects in components with complex geometries produced by additive manufacturing processes. They manufactured the component that you can see on the screen, which is about 140 millimeters in sort of length and height, specifically for this project. The sample is made out of stainless steel and was made via selective laser melting. After the component was manufactured, a small flat bottom hole was drilled into the side of the sample to create a known defect. When we got the sample here at CEMAS, the HeliScan was set up with the Lab 6 filament, so it was more suitable for high resolution, low flux imaging. This meant that we were limited to using a maximum tube voltage of 100 kilovolts. However, even with having that limit, we were still able to penetrate the sample and obtain a very usable data set. The sample was mounted vertically to minimize the thickness of the material the X-rays had to penetrate through. This resulted in one scan capturing about a quarter of the total component size. The reconstructed data set, and you can see a slice, a vertical slice from it here, had a voxel size of about 64.3 micron, and the scan took about 5 hours. From visual inspections of the tomogram, a slice of which you can see on the screen, we were able to clearly identify the flat bottom hole here. And this picture here is just zoomed in this little red area. We were also able to identify this little crack. So this scan really showed that for samples of this geometry and density, we are able to use the HeliScan to detect defects of the samples of the size of this flat bottom hole. And I believe the flat bottom hole was about 4 millimeters in diameter. So that brings us to our final case study for today. This animation was made by Felix Liu, who is in Dr. David McComb's group at Material Science and Engineering and also CEMAS, in collaboration with Dr. Brewer at Nationwide Children's Hospital. Felix is working to characterize the pulmonary valve, the pulmonary heart valve in mice using a correlative imaging workflow. The mouse hearts are fixed, stained, dehydrated, and finally embedded in resin. This process is required to ensure sufficient contrast for microscopy techniques like MicroCT, SEM, and TEM. However, information about the spatial orientation of the pulmonary valve is lost during this process. Felix uses the HeliScan MicroCT to gain spatial information about his sample. This animation starts by showing the resin block as a whole. It will then highlight the mouse's heart. And then the pulmonary valve will be highlighted in green. Once the location of the pulmonary valve is known, it is possible to precisely microtome into the sample to capture this feature. In this animation, an ortho slice showing the CT data is used to represent the sample being cut down. Then we zoom into the sample to show higher resolution SEM images of the valve. So that was the last of our 5 case studies. I hope you found them interesting and maybe a bit insightful and like a bit inspiring maybe to come and use the CT. Thank you for joining me today for the second Beyond the Scope CEMAS Discussion Series. Next week, Daniel Vecti will be presenting about seeing beyond postmortem in situ capabilities of ESEM. You can register on the CEMAS events webpage.